think we can go ahead and get started. Hello, everyone, and welcome to this CUAHSI Cyberseminar Series, Research and Observatory Catchments, the Legacy and the Future. CUAHSI is very excited to host this series, which was convened by Jamie Shanley, U.S. Geological Survey, Stephen Sebestyen, USDA Forest Service, Giulia Jones, Oregon State University, and Theresa Blume, GFC Potsdam. My name is Ainsley Brown, and I'm the Communication Specialist for CUAHSI. CUAHSI is the consortium of universities for the advancement of hydrologic science, and our mission is to advance water science by strengthening interdisciplinary collaboration, providing critical structure through our data services, and promoting education in water science at all levels through programs like the Cyberseminar Series. And I would encourage you all to reach out to me, visit our website, and or sign up for our newsletter to learn more about what we do or to get involved. And I will be adding more information on all of those things to the chat in just a few moments. So this webinar series will be recorded and will be posted on the CUAHSI YouTube channel tomorrow. If you'd like to check out previous week's recordings for the first few webinars in this series, please visit youtube.com/CUAHSI. And if you do have any questions, please remember to put them in the chat, and there will be time for a brief Q&A after each presentation. And then we will have a longer discussion at the end. So we will do our best to get to as many questions as possible. So thank you all again for joining us this week, and we look forward to hearing your thoughts during the discussion at the end. This week's topic is seasonally snow-covered temperate catchments. And with that, I'll go ahead and hand things off to our convener, Giulia Jones, who will introduce this week's topic and first speaker.
Welcome, everyone. It is so great to have such high attendance. This is the fourth week of the series, and we've had exceptionally high attendance and excellent questions. Just a reminder that the purpose of this catchment series is to introduce us mutually to all the amazing work that's going on around the world, and in particular to increase our understanding of catchment studies that may be less well known or newer, as well as the new items or new bits of research going on at well-known catchment studies. We have a 15-minute discussion period from after the end of the talks. And then also in week 8, we will have a full session of a discussion period. And so we ask you to think about common themes and ideas for where catchment science should go in the future as you listen to these talks. Jamie?
Thank you, Giulia. And we have up our world catchment map here, with today's presentations denoted by red dots, and there we go. And the previous week's presentations in yellow, and the black dots are all the catchments around the world that we've been able to identify and put on the map so far. And this map will be featured in the special issue of Hydrologic Processes that many of you have contributed to. So, this is week 4, and I thank everyone for their presentations so far and the ones today. Because of the interest in this series, we are having a lot of short presentations. These are going to be 6 minutes. And without further ado, I'm going to launch right in with Hjalmar Laudon.
Jamie, actually, maybe a little bit more ado from me. Welcome, everyone. I just want to remind you to enter your questions into the chat. Panelists will see your questions. The audience will not see your questions. We might respond during the first hour here, but front load questions for the individual sites, the individual speakers, and discussion points for the end. We'll work on it all behind the scenes, and hopefully we'll be able to address everything by the time we wrap up here. Thank you.
Thanks for that ado, Steve. And I wanted to say Hjalmar would have been in last week's session on the boreal catchments, but he couldn't make it. So he's going to introduce our remaining temperate catchments. So take it away, Hjalmar.
Thank you very much. It's a pleasure to be here, and I thank you, the organizers, for this and for the invitation to be part of this great session. And incredible presentations. I've actually watched the last one as well. I did have time to see the whole thing, which has been great. So thank you. But I will take you on a little tour to northern Sweden. And as we talk about seasonal snow-covered systems, I think this fits nicely in. This is a catchment in northern Sweden with on average 167 days of snow cover. Changing quite rapidly though, and I will come back to that. Perhaps not so much to snow specifically, but from other items that are changing in recent times. The Kryklan Catchment or the Svartberget Catchment is a field research infrastructure to really try to understand, we could say, the integrated questions related to hydrological, biogeochemical, atmospheric, forestry, ecological questions. So we really try to take, sorry, now you're moving quite quickly there, thanks. This is the text tries to integrate all these questions in one catchment system consisting of 67 square kilometers it's been long-term research infrastructure ongoing for about 40 years. It has, as you can read, 15 monitored catchments, 200 groundwater wells, a lot of different things here, and I'll come back to these things. But I would want specifically point to two very important things here. It's very, very skilled technical staff and very many scientists from all over the world participating in the research that is ongoing. So next, please. So I talked about a landscape in transition, and that's really what I wanted to show here is some things that are quite rapidly changing in this landscape. One is the warming climate, and this is a reconstructed climate record that we have from this site, spanning from 1890 to present. And you could see the very dramatic increase, especially the last 40 years here in temperature. And especially the warmest year ever of 4.1 degrees occurring 2020. So things are changing quite rapidly when it comes to temperature. Next, please.
You have 3 minutes.
Okay. Deposition is changing rapidly, so as you can see, when it comes to deposition load. Next, please. Tree biomass is changing quite dramatically. This is showing the tree biomass in the catchment relative to 1957. As you can see, it's increased by 60%. Next, please. So these are things are changing, and what can we do? Well, Kryklan really has 3 different programs. One you call the atmospheric program, and it's based around this 150-meter atmospheric tower, looking at carbon emissions and water vapor. Part of the ICOS integrated carbon observatory system, which is similar to the American Flux system in the US. Next, please. We have the Kryklan Forest Program, which consists of a lot of different forest-related questions in forest inventories, forest development, LiDAR development, and the last new addition, that is the new radar tower that is being built as we speak. That's 130-meter high tower that will look at the canopy changes and the vapor in the canopy. Next, please. And then we have the Kryklan Water Program, which consists of these 15 long-term monitor sites. It has an evapotranspiration process module. We do a lot of water landscape analysis and a groundwater program related to the 200 groundwater wells, the deepest being 150 meters deep. So a lot of new work on the groundwater system that is being developed. So with all of these things, we try to really take an integrated perspective over this landscape. We understand why these changes occur and what they mean for hydrological, biogeochemical, and ecological questions. Next, please. So I really want to more or less end with this picture here, because it's one of the things that we really enjoy is students coming to our site, participating in different activities. And one of those activities that we have is the Watershed Ecology and Biogeochemical PhD course. Master students are also welcome. It's a week-long or 10 days long program with that goes from 15th of September to the 22nd of September and ends with the Kryklan Symposium that we have every year. This is a great opportunity to see what we do, understand some of the processes up in this quite northern location, and also meet other PhD students. So you can read more about this if you're interested at our homepage, slu.se/Kryklan. Next, please. Well, yes. So I'll take any questions if there's time.
Hjalmar, we haven't received any questions or discussion points, and I think for timing, we're about ready to go on anyway. But if you have questions for Hjalmar, do enter them, and we'll try and address them through the chat or in the discussion at the end.
Great, thank you. Thank you, Hjalmar. Next up, we have Giulia Zuecco from Italy. Go ahead, Giulia.
Thank you very much for the invitation and for organizing this series of presentations about experimental catchments. So I'm here to introduce you to the Ressi experimental catchment, which is a really small catchment in the Italian pre-Alps. And it was a catchment established by the Hydrology group of the Department of Land, Environment, Agriculture and Forestry of the University of Padua, Italy. Next, please. So the catchment was established in a pre-alpine area where there was a massive abandonment of the agricultural land and a consequent expansion of the forested areas. So there, our main questions that we want to answer are how much the transpiration rates have changed in the last 30-50 years, and what is the impact of land use change on flow regimes and water resources. Next, please. The main objectives of our research are to investigate the role of ecology on the hydrological response of the catchments and the geochemistry of the surface waters, then to evaluate the influence of vegetation on the hydrological response of our catchment, and determine which waters are mainly used by the vegetation for transpiration. And finally, also to estimate young water fraction and transit times by means of isotopic data and modeling approaches. Next, please. So our Ressi catchment is a subcatchment of the Posina River catchment, which is located in the eastern Italian pre-Alps. And the Ressi catchment is surrounded by a network of weather stations and stream gauge stations run by the environmental agency run by the region, the Veneto region. Next, please.
You have 3 minutes.
Yes, thank you. So the Ressi catchment has 2 hectares area, and the elevation range between 600 meters above sea level and about 720. And it's a catchment in a humid, temperate climate, and average annual precipitation is about 1,700 millimeters per year. And it's a forested catchment characterized by a narrow riparian zone and steep slopes. Next, please. This is our hydrometric and tracer monitoring. So we measured discharge at the outlet of the catchment, and then we monitor soil moisture at different locations and depths, and the shallow groundwater depths at 6 pisometers. Next, please. We monitor we collect water samples for isotopic analysis, electrical conductivity measurements, and measure ions analysis. Next, please. So here we have an example of a few results that I'm giving a brief overview. So we observed so far a strong seasonality in both the runoff response and the soil moisture at the different locations in our catchments. Next, please. And this is our data set that we have collected from 2012 to 2018. So there is a large variability in the isotopic composition of the different water sources. There is a good alignment to the local meteoric water lines, but we saw some deviations from the local meteoric water line for the saltwater samples collected by cryogenic vacuum distillation. Next, please. Based on the isotopic data and electrical conductivity data, we have performed free component hydrograph separation, and we found that also here there is a strong seasonality in the contribution of different water sources, with groundwater in the riparian zone and precipitation contributing more during dry conditions, while slope soil water contributes mainly during fall events. Next, please. Then currently we are working more on the identification of the end members. So we're putting together the different tracers and information coming from the major ions together with the isotopes. And we are also interested in observing the spatial and temporal variability in the tracer composition of the riparian and the hill-slope groundwater. Next, please. Then here we have the event dynamics. So we are basically running this analysis for 20 rainfall runoff events collected between 2015 and 2018. So these events are characterized by different conditions of total event rainfall and antecedent wetness conditions. Next, please. And finally, we are also working on the hysteresis. So we are also interested in identifying the main controls on the hysteresis between the tracer concentration and the stream flow for the different events. So in this case, to highlight whether we have flushing or dilution processes. Next, please. So thank you. So if you have more questions and you're interested more in our catchment, so please also see the publication that was recently accepted for the special issues on hydrological processes on the research and observatory catchments. Thank you.
Thank you, Giulia. I think we're going to move on to the next presenter.
Great. We'll go right to Cara Webster. The rest of our talks will be in North America, starting with Cara at Turkey Lakes in Canada. Go ahead, Cara.
Thank you. So welcome to the Catchment Speed Dating Turkey Lakes Watershed edition. And we have recently celebrated our 40th anniversary of interdisciplinary whole ecosystem monitoring and research. Next. So some of the key features of the watershed is that it's hardwood dominated, over 90% sugar maple, total annual precipitation of about 120 centimeters, with about a third of that falling as snow. So that results in peak stream flows occurring during the spring snow melt, about 300 meters of elevation relief. And the soils are relatively shallow podzels or spodzels overlaying bedrock at the high elevation and till at the lower elevation. And interesting feature is small bedrock control swamps are common and play a role in the hydrology and hydrochemistry. Next. So the Turkey Lakes Watershed is at the northeastern edge of Lake Superior. It's 10.5 kilometers square, and it's composed of a series of 5 interconnected lakes. The Canadian Forest Service monitors 13 headwater catchments, 2 meteorological stations at the upper and lower parts of the watershed, and vegetation and soil permanent sample plots. And the Environment Canada Water Division monitored lake outflow and some groundwater up until 2019, but unfortunately have since stopped this monitoring. The area showing as red is an experimental harvest area that was undertaken in 1997 that applied clear-cut selection and shelterwood harvest treatments. And then down at the bottom right there, the Environment Canada Atmospheric Division operates a Capmon deposition site just outside of the watershed. And there's also a base camp near that Capmon station, and we have supporting analytical labs at the Great Lake Forestry Center in Sault Ste. Marie. Next. So the Turkey Lakes watershed was really born out of the acid rain era, but as you can see by all the circles on this slide, there has been research and monitoring of many different ecosystem components in response not only to acidification recovery, but also to climate change and forest harvesting disturbance. There's been both the long-term monitoring, but also many, many short-term studies. Theory has been advanced as well as applied science done. There's been lots of site-based studies, but also the watershed has been part of regional and continental syntheses as well. And this has been done using both empirical and modeling studies. So one of the strengths that I think the Turkey Lakes Watershed has is that we've been able to adapt to changing priorities to try to remain relevant. Next, please. So in our roadmap of where we want to go, we hope to maintain the baseline monitoring to continue examine trends. We also hope to continue process-based studies to understand the mechanisms behind the long-term trends. We hope to be able to better understand how processes scale from the headwater catchments to the watershed to the basin and beyond. And also to better integrate fluxes of key nutrients along the upland, wetland, stream, and lake ecosystem continuum. And of course, we want to do this all within a cumulative effects framework to understand how climate change and other disturbances interact. Next. So we've had many successes and challenges at the Turkey Lakes Watershed. Some of the successes, the whole ecosystem approach has been very useful, and it's been very interdisciplinary. We have over 400 publications and almost 500 different authors. Many partnerships have been developed, over 25 from government, academia, and industry. And as I've already mentioned, we've been nimble in trying to respond to changing priorities and contributed to many synthesis papers. And we've also contributed to training and education of many students. 23 theses have been specific to Turkey Lakes Watershed. And we're finally starting to get some of our core data sets to our open data repositories. In terms of the failures, like many catchments, data management is our Achilles heel. We have never had a dedicated data manager, which of course brings us to the never-ending fight for fundings, for operations and staff. We really do have a shoestring budget, and we have retirements in key positions that aren't being refilled. And the loss of the Environment Canada Water Division to partnership has been a recent concern, and this leaves a large gap in the ecosystem data set at Turkey Lakes. We also have site scale challenges of being off the power grid and not having telemetry. And another key point that I wanted to point out is that in Canada, unlike the US and Europe, we do not have a nationally coordinated network of long-term ecological sites. So long-term sites like ours can easily fall victim to cuts. And the last point is about communicating relevancy. And as much as we try, not everybody is like this group, and not everyone seems to get the value of what we do. Next. So I'd like to encourage you to reach out to us if there's aspects of this research that interest you. Below, I've listed some of the key researchers involved in different aspects of the Turkey Lakes work. And I'd also like to acknowledge that many visionaries have come before us and have shaped this incredible watershed study, for which we're very thankful. Last slide. So finally, I'd like to point out a few other resources you might be interested in. As part of our 40th anniversary celebrations, we developed a video of the Turkey Lakes Watershed with some great drone footage. We also have a research compendium in press. And so if you're interested in it before it's produced, I'll send you a draft copy. I've also listed some of the key data sources. And I'll point out that we do have a data note appearing as part of the special issue. And we also have a research paper on long-term trends in stream chemistry. And finally, I provided the link to the Turkey Lakes website, which is actually going to be updated soon. So thank you very much.
Thank you very much, Kara. I really appreciate your clear articulation of the successes and challenges. I think that was great, and I wish I had done the same. I'm taking this to mean that we're out of time for questions, but one was posted in the chat if you want to attempt to address it, Kara. I am the next speaker, so I'm going to go over the research program at the Mchale Experimental Forest, which is in north central Minnesota in the USA. We operate 6 long-term catchment studies as part of a basic research program within the Forest Service Experimental Forest and Range Network. And that includes about 20 watersheds that are spread across the US. we are different because of our basic landscape feature of having peatlands in each of our watersheds. So to this point, we've done quite a bit of research on organic soils, what they are, why they matter relative to mineral soils, basic ecology of these ecosystems, chemistry, and hydrology. And as far as I know, we are the longest ongoing monitoring program of catchments with peatlands on the entire planet, having started in 1960. So that monitoring now really helps us to document ecosystem responses to land management and environmental change. And we've done a number of large scale experiments to study the effects of environmental disturbance on these ecosystems. Within that framework, we do a lot of networking. We're very collaborative, always have been, and we share our data. The photo at the bottom kind of shows a heyday of 1972 with a strip cutting experiment on one peatland, a clear cutting and revegetation study on a fen in the background, as well as our reference base in the S2 basin, and some other sites where we've since done a forest conversion study, a hill slope mercury tracer test, a drainage study on a peatland as well. Next slide, please. And again, to highlight, these are lowland catchments along the southern edge of the boreal peatland zone. And that's a great photo inset where you can clearly see the peatland defined against the surrounding upland landscape, the hardwoods in that landscape, and then the peatland with its sphagnum, tamarack, black spruce community on there. We are the headwaters to both the Gulf of Mexico with flow via the Mississippi River and the Hudson Bay via the Red River of the North and other systems that go there. Next, please. We encapsulate a range of peatland types as well, and that really spans the gradient from minotrophic or groundwater fed peatlands that are mostly depressions in the landscape that over 10,000 years since the last glaciation have infilled with organic matter, to systems that are raised dome ombrotrophic bogs or rainwater fed systems that they do recharge water to the aquifer in that outwash sand, but they do have a perched water table that's completely separate. So in the case of that middle diagram, it's showing a difference of 1 meter of water level between the peatland water level and the surrounding aquifer in our S1 bog, to the contrast to that, which is nearly 7 meters of hydraulic head in the S2 bog that's above the regional aquifer or the surrounding groundwater aquifer. Now the bottom panel just shows a flow duration curve showing that the fens and the bogs actually have the same peak discharge magnitude, but they're very different under low flow conditions. It's intermittent flow in the bogs, and they only have flow, or they have no flow for 24% of the time, whereas there's always a base flow in the S3 groundwater fed catchment. Next slide, please.
You have about 2.5 minutes.
Thank you, Giulia. So we have a continental climate with wide-ranging temperatures from the low of -46°C to +38°. We do have that deep glacial aquifer with a 50-meter outwash sand. There's little topographic relief on any of the catchments, less than 10 meters, and the catchments range in size from 10 hectares up to 70 hectares. These are natural undrained central peatlands, except for the peatland that we drained in an experiment. They are the black spruce vegetation communities, and the upland forests grow on mineral soils. Next, please. They are highly instrumented catchments. We've spent a lot of time trying to decipher the sources of flow, and we've apportioned it into about 58% of the annual stream flow comes from 33% of the catchment area, and that's the peatland. So it's rapid infiltration excess flow from the peatland surface relative to the surrounding uplands, which are actually larger in area. There's 67% of the catchment area for our S2 peatland or catchment, but it only contributes 42% of the stream flow. There is some infiltration excess overland flow over frozen soils, but most of the flow from the uplands of the peatland occurs as subsurface storm flow. Next, please. We are monitoring change at this point. So over 5 decades, we've seen a 2.5-degree increase in mean annual air temperature, longer growing seasons, and earlier center of mass for snowmelt. Corresponding to that, we also see a giant change in total organic carbon concentrations with a near doubling, high background concentrations in the early 1980s and a doubling over that time period to about, it ranges from about 40 part per million at the beginning of the record to about 80 part per million now. So a lot is happening in this landscape due to environmental change. Next, please.
You have just under a minute.
Thank you. We've also done a number of paired watershed studies. So again, the diagram here shows our different landscape elements with the peatlands in there, and the photos in the bottom illustrate the 1960s when we had an upland forest cover on the S6 catchment, which is in the background, and we converted it to a conifer cover by the 2010s. So an example of many with the others listed on the side. Next, please. And we've also done a tremendous amount of carbon work over the land. So hotspots of carbon storage in the peatlands, some of the first methane emissions from northern natural peatlands done in the 1980s, state-of-the-art advancements with the first implementation of eddy covariance measurements, and that's ongoing work now. That's part of the Ameriflux network. Next, please. And our biggest thing is the spruce experiment. We've shared our data, and we should move on with that.
No time to ask yourself a question, Steve. So we're going to move right on to Sherry Johnson. Will take us out to Oregon. Go ahead, Sherry.
Hi. Today I'd like to share a brief overview of some hydrology core data from the H.J. Andrews Experimental Forest, which is located in the Cascade Mountains of Oregon. Many researchers have contributed to increasing our hydrologic understanding over the years. And today I'm just going to highlight a few studies that talk about our hydrologic responses to changes in snow, precipitation as a result, and thinking about climate change. Next. The Andrews Experimental Forest was established in 1948 and became an LTR site in 1980. It's conifer forest with about 2,200 millimeters of precipitation. Elevation ranges from 420 meters at the mouth of Lookout Creek there to the ridges about 1,700 meters. So it really is a rain-snow transition zone. Within the 6,400 hectare basin of Lookout Creek shown here, we've had several paired whole watershed experiments. These were established between 1950s and 1980s. Within each pair or triplet, we have reference and harvested watersheds, several groups at low elevation and one group at high elevation. We also have gauged Mac Creek, which is an primarily old growth, a much larger watershed. And at the mouth of Lookout Creek, USGS maintains a gauge and Andrews samples chemistry. Next. We submitted a data note to the HP special issue, and thanks to the organizers. These are the topics that are covered: discharge, stream and precipitation chemistry, and climate. Also available in addition are snow SWE, snow depth, distribution, stream temperature, and distributed temperatures under canopy. Much more data in addition to these are available on the website shown here at the bottom of the page, as well as through EDI and Data One, which is part of the LTR data repository. Next. As I mentioned, Andrews is located in a transition zone of rain to snow, and many papers over the years have examined forest management effects on snow and discharge. However, as we look forward, the IPC has been proposing that in this region, with climate change, we're going to see a decrease in the amount of snow, and they're also projecting much variability in the timing and amount of precipitation going forward. Several researchers are beginning to use long-term data and planning new studies to begin to explore to what extent does the form and amount of precipitation impact recession curves, summer base flow, soil moisture, and what are likely influences or potential mitigating factors to help us understand these variability in responses. Next.
You have just over 3 minutes, Sherry.
Thanks. Several researchers that I'm highlighting today are using a drought that we had in 2015. This is a graph showing long-term averages at Lookout Creek, created by Steve Wanzel. If you look closely, down at the bottom, you see the red line that shows the 2015 discharge. It was much lower precipitation during our normally wet months of November through April, and then with very little precipitation from March forward. Next. If we focus on the slow flow time, you can see that at Lookout Creek, it was some of the lowest flows ever observed. Next. However, if we look across basins, we see that there are some variability in these responses. Watershed 2 is a small old growth basin at low elevation, And the discharge in 2015 was more at about the 10th percentile. Next. Catalina Segura and colleagues have been using variability of 018 during this drought period to look at the sources of water and have shown that groundwater springs and Upper Lookout provide the majority of flow and have a substantial influence of the 018 signal. Next. Adam Ward and collaborators have been extrapolating from our stream gauges and doing modeling up to the full stream network to think about the frequency of length of flow across the stream network. They're seeing that in late summer, there's been a decrease over time. Other teams are validating this model by doing flow permanence measurements across the headwaters. Next, please. So in addition to the 2015 drought, we've had other extreme events recently, and these are projected to become more common with climate change. In 2018 and 2019, there were windstorms as well as heavy snows, and some researchers are just beginning to examine how responsive was discharge to this toppling and mortality at low elevation areas that normally don't have this heavy snow. In September of 2020, we had fire, of mixed severity, which entered watersheds 1, 9, and parts of watershed 2. Much planning is going on to be looking at the effects of these other disturbances. And we encourage anyone interested to make use of the long-term data as well as data from newer studies and to join us in these explorations of what climate change and extreme events might mean. Thank you.
Thank you, Sherry. We have a pretty good discussion going on in the chat. Keep those questions rolling in and we'll address them as we can. Now we're going to move on to Jamie Shanley and the Sleepers River Research Watershed.
All right, thank you, Steve. And I fully acknowledge I have a very corny title, but I think this is a really good analogy that a lot of us find the biogeochemistry to be very compelling, but where would we be without the hydrology to understand how water is moving solutes to the stream? Next, please. So Sleepers River, if I can direct you to the upper right corner, our location map, we're kind of in the middle of a triangle formed by the cities of Montreal, Boston, and New York. But we're far enough away from those cities where we're in a very rural environment. And our main watershed that we work in is the W9 watershed in the headwaters. There's a blow up of it on the upper left. And if you look at the entire Sleepers River watershed on the right map, the entire watershed is 111 square kilometers. And we have kind of a nested basin design with W9 in the headwaters. There's photos of these on the bottom. And going up in order of magnitude to each next scale, W3 and W5 is the entire watershed outlet. And each of these, yes, is an order of magnitude larger than the last. And we also have the W2 catchment there in the middle, a small agricultural catchment I'll touch on in a minute. Next, please. So we do have a fantastic history of hydrology at Sleepers River that started well before the USGS got involved. The research watershed started in 1959, and we had these luminary hydrologists who set the path for our biogeochemical work. So Eric Anderson with the National Weather Service did some of the early energy balance snowmelt modeling, and some of the algorithms he developed are still in use today by the National Weather Service in flood forecasting. So they had a great research site there that we are maintaining now a little bit. And they took advantage of the gauged watersheds to look at, how melt was transformed into runoff. And then Tom Dunn with his landmark studies on partial contributing areas in the late 1960s into 1970. And this lower right photo shows Tom back at Sleepers River for the first time in 2001, where they had entirely removed his hill slope study for a highway widening project. And he's standing in the median strip going, where's my hill slope? And then we benefited from Jeff McDonnell and students in the 1990s when we just started at Sleepers River and, forming the, some more fundamental hydrology that inspired a lot of our later work. Next, please.
You have about 3 minutes, Jamie.
Okay, thanks, Giulia. So one of our pride and joys is our snow record. It's one that we inherited and we've been able to keep going. So we have a continuous record since 1960 on snow depth and water equivalent. Next, please. And I wanted to just kind of go over some of our infrastructure. We have the 3 active stream gauges. We have 8 meteorological stations along an elevation gradient where we measure our snow courses and some of the meteorological parameters. And how we are building on Eric Anderson's early work is, like a lot of the snowmelt work is based on measurements in the open. We're now going into the forest because most of our landscape is forested. So Dave Chandler at Syracuse has a lot of instrumentation going to look at how the melt process proceeds in the forest with cell phone transmission of data. We also have 13 abandoned weir structures around the basin, 44 wells in W9, and in-stream measurements, zero tension lysimeters, soil moisture, and a place for students to live if they want to live for free, a cabin. Go ahead, next slide, please. I just want to touch on a little bit of the research. We are looking at stream flow generation, flow paths, and solute sources. Organic carbon has been a big part of our research, especially in the past decade, and along with mercury extreme events. And now we are trying to scale from the small watershed all the way to the ocean. Next, please. And 3 slides on just a few research topics. We've done a lot of 018 work with Jeff McDonnell and crew early on and continued that on. And we see a huge damping. The red in the upper left photo, the red is precip, and 4 different streams shown sort of bisecting that middle, where that damping translates into 8-fold decrease in the standard deviation, which translates to a 1.3 mean residence time for water in the system. But on occasion, when we get frozen ground and we are measuring ground frost depth, we see, that infiltration can be eliminated and that water runs off over land. So you see the stream following the meltwater signal in this agricultural catchment. And so the depletion in isotopes in that one winter corresponds to the purple line to the right of the left plot. So obviously in those 8 years shown, we didn't get anything like that. So this is kind of an anomaly. Next, please.
You have 15 seconds.
Okay, just finish with this one or this one. So we are now doing a lot of sensor work and looking at hysteresis and the dissolved organic carbon signal. Thank you. Okay.
With that, we should move on to the next speaker.
Right. So next we have Mike Mchale from USGS talking about Biscuit Brook. Go ahead, Mike.
Biscuit Brook. Okay. Research in Biscuit Brook began in 1978 with the installation of a National Atmospheric Deposition Program station. NY68 still there today. We also monitor mercury deposition there now. Pete Murdoch started monitoring water quality in Biscuit Brook in 1983. That's continued to this day. Biscuit Brook, I think it's in the top 3 or 5 of the most sampled streams in the USGS. If you look in our NWIS database, Biscuit Brook has more samples pretty much than anybody else. That's Pete. He's a good man and thorough. There's been a long list of collaborators that have worked in the watershed over the years. Just within our office, I think I kind of did a quick count of maybe 30 different people who've worked in Biscuit Brook over the years, plus many other folks. Next slide, please. Biscuit Brook is located in the Catskills of New York State. If you look at the little New York State map there, it's in the southern tier. It's 9.6 square kilometers. There's 6 surface water reservoirs in the Catskills that account for 90% of New York City's drinking water supply. It's the largest non-filtered drinking water supply in the world. Biscuit Brook is in the headwaters of the Neversink reservoir catchment. In 1991, 3 additional Headwater streams were added to the long-term monitoring. They're funded by the EPA to track stream water chemistry in response, changes in stream water chemistry in response to Title IV of the Clean Air Act amendments. Winnisook, which drains Slide Mountain, which is the highest peak in the Catskills. Also Teeson's Creek and Rondout Creek in the Rondout Reservoir. We also monitor the inlet to the reservoir upstream from any influence of backwater. That's been monitored since the 30s. There's a list of all the different types of data on this map here that we're collecting. We also have an ET tower that was recently installed. The Neversink is the most acidic of the 6 reservoir watersheds. How acidic? Next slide, please. This is acidic. As you can see, Winnisook is, they range from what I would say is moderately acidic to pretty chronically acidic, with Winnisook being the most acidic. Biscuit Brook falls in the moderate range. Why are these watersheds so acidic? The Catskills look like mountains, but they're not really mountains. They're actually composed of nearly flat-lying siliciclastic sedimentary bedrock from the Devonian. It's an uplifted deltaic plateau that's been dissected by streams to form some really steep topography. When you're hiking them, they certainly feel like mountains. The bedrock and the soils are very calcium poor. They've been subjected to decades of acid rain, and the result is soils with very low buffering capacity. Next slide, please.
You have about 2.5 minutes.
Thank you. So one of the focuses of research in the watershed is trends in acid deposition. The Clean Air Act has had a huge impact on the region since its passage. This has resulted in a decrease in stream sulfate and stream inorganic monomeric aluminum concentrations, which has a lot to do with fish habitat. In fact, Barry Baldigo has been finding brook trout in Winnisook since about 2012. And during the 90s, we didn't think we would ever see brook trout again at that site. There are many, many other studies that have been conducted in these watersheds. Doug Burns did a bunch of nitrogen dynamic work in groundwater seeps in the hyporheic zone in the 90s. Greg Lawrence did a bunch of episodic and chronically acidic stream work in the 90s. Barry Baldigo, as I said, has been doing fish sampling for more than 30 years. Pete Murdoch was really the one who got this all started, his work in the episodic response project in the 90s, and there was a series of forest harvesting experiments that occurred in the 90s and 2000s. All of us participated in that. This is a paper that is one of our most recent efforts. The interpretation has never really been funded for this work, so we string that together as best we can. Next slide, please. What's going on now, the USGS has a new program called the Next Generation Water Observing System, or NGWAS, and the Delaware River was selected as the first watershed in the program to be studied. The focus is on providing better data to watershed modelers, especially in terms of better water balance estimates. And so there's a bunch of different watershed measurements that are being collected now as part of the NGWAS. I started with the USGS in 1997, and I've basically been involved in this watershed during that entire time. I took over primary responsibility for keeping this work going when Pete moved on to a more national role. And I've done my best to keep it going with a lot of help from a lot of other people. We'll keep it going as long as funding allows. Next slide, please. And I'll just end with saying that these are the major funders of this research: the USGS, the EPA, NYSERDA, the New York State Department of Environmental Conservation, and New York City DEP. And I just wanted to point out that it's because of places like Frost Valley, who own most of the land, and like the Teeson Family Trust, that we're able to do this work. So I just wanted to acknowledge that those folks are extremely important to getting this kind of work done. Thank you.
Thank you, Mike. There is a lively discussion going on, so keep the questions coming and look at the answers that have been posted. Jamie?
Okay, so next up was Scott Bailey, but Scott could not make it today, so Mark Green is going to fill in. You might remember Mark gave a talk 2 weeks ago in this series. Go ahead, Mark.
Yeah, thanks, Jamie. Yeah, and I'm going to fill in for Scott to talk about how we've used spatial sampling of streams within the Hubbard Brook experimental watershed to better understand processes that are occurring in these small catchments. So the work is happening at the Hubbard Brook Experimental Forest in the White Mountains of New Hampshire, as this photo shows. It's a deciduous forest, predominantly with seasonal snowpack, relatively cool and moist. The research program has largely been focused on 9 experimental catchments where we've done water and solute budgets with a pretty rigorous acid rain research program going. So it's going to be the focus of this talk. And just to acknowledge that this has been a collaborative effort amongst many people. All of the data that I'm going to be presenting here is available at hubbardbrook.org. Next, please. And so we've used synoptic stream surveys pretty much since pretty early on in the study. Noy Johnson in the 1970s started to monthly sample Falls Brook from the top of the ridge to the bottom of the valley to look at how the acidity had changed, to develop some ideas about that. The follow-on, Gene Likens and Don Busso sampled the entire valley to see the spatial variability of pH and notice just extremely broad range in the acidity, which gave us, some hints at some different processes happening across the valley. Margaret Zimmer's undergraduate thesis, which was published in 2013, she dug into Watershed 3 and showed that we see as much spatial variability in water chemistry within Watershed 3, this small catchment, as we do at the whole catchment, or at the whole Hubbard Brook Valley scale. So we followed up on that and looked at a few smaller catchments or a few other small catchments to see the end members of very acidic to less acidic catchments to try to understand soil processes. Please, next.
You have just over 3 minutes.
Yep. So here's Noy Johnson's idea of why spatial chemistry or spatial stream water varies. So high acid deposition at the top of the catchment. We see partial neutralization as water flows downhill and interacts with aluminum. And so that weathers base cations. So we see base cation concentrations increase as we go down slope. Next, please. And so work by Scott Bailey, Kevin McGuire, and others, they've come up with this understanding of how lateral water transport in the subsurface of our catchments contribute to soil development processes in a lateral sense. So at the top of the watershed, we see a low pH arising from very high dissolved organic carbon. So these are mostly driven by high organic acids causing weathering processes to occur at the top of the catchment. And then we see those mobilized base cations and aluminum being deposited as we move further down the hill slope. And our spatial stream water sampling matches some of the spatial soil mapping that's been done in Watershed 3. So these synoptic surveys have been extremely helpful in developing hypotheses about the spatial variability of soil types and the soil development processes. Next, please. And so we can revisit Noy Johnson's model of weathering of bedrock as we move down the hill slope. And instead of the high acid deposition, we would replace that with high organic acids coming from those shallow soils at the top of the ridge that are weathering plagioclase, and which is creating calcium, sodium, and aluminum, which is then being deposited further down the slope, which drives the spatial variability of pH and weathering byproducts. And so our patterns match noise just with a different source of acidity in this current era. Next, please.
You have about 30 seconds.
Yep. And so to wrap it up, we have gone from, and we still think about catchment solute budgets to understand the biogeochemistry, but these synoptic surveys have given us much better understanding of the spatial variability and the processes that are at play within these catchments and drive our solute budgets. And so we're opening up the black box through these tools. So with that, I'll thank you.
Thank you, Mark, for presenting on the behalf of Scott, who pulled together those slides. I really appreciate the last minute substitution.
Yep.
We're going to move on at this point, but there is that lively discussion. Keep the questions coming.
Great. Okay, thank you, Mark. And last up, we have Jeff Pooh from Syracuse, who will also be talking about Hubbard Brook.
Thank you, Jamie. So our work also focused on Hubbard Brook, and thanks, Mark, for the introduction to save me a couple of minutes here. And our work focused mainly on quantifying uncertainty in stream solute fluxes. Next slide, please. So our project focused on answering these key study questions. What are the different uncertainties, the sources, and determining what is the overall uncertainty in the stream fluxes, as well as looking at whether the uncertainty differ by solute, as well as looking at what is the main uncertainty source here. And I just wanted to also mention that the main motivation for this project was that we found that a lot of the small watershed report these solute fluxes, but few have reported uncertainty that were propagated through that solute fluxes. So this was the main motivation for this project. Next slide, please. So this is just showing you the different uncertainty sources that we looked at. On the stream flow side, we looked at the watershed area rating curve, in other words, high discharge relationship, and gaps in discharge in terms of uncertainty introduced by how we fill in the gaps for those data that were missing. On the chemistry side, we considered the chemical analysis, so the lab QC variabilities, as well as the concentration discharge relationship. Next, please.
You have about 3 minutes.
Okay, thank you. So this is showing you one of the uncertainty that we considered, the state high discharge relationship. And as you can see, the calibrated relationship is different from the theoretical. And this is one aspect of the uncertainty that we incorporate into the final uncertainty quantification. Next slide, please. So this is showing you the uncertainty in the concentration discharge relationship. And obviously, as you can see, all the different elements have different relationships. Some of these have stronger relationship, such as the silica, and some of them do not have quite strong relationships, such as potassium. And we can also see that some of these relationship is positive and some of them are negative. The yellow shaded ones are the ones that we determined or have strong enough relationship for us to predict concentration using discharge. Next slide, please. So this is the flow chart of the entire analysis. Obviously, I would not expect you to read through every single details here, but I would like to point out the blue shaded areas are how we incorporated the discharge uncertainty, and the light brown shaded area is how we incorporated the chemistry uncertainty. And at the end, we quantified the uncertainty on flux by combining these all of these different uncertainty sources. Next slide, please. So this is showing you the preliminary results that we have so far for the 4 different elements. As you can see, the uncertainty differ by different elements that we are looking at. Lab uncertainty having the highest amount of contribution to the uncertainty in flux. And as you can see, there are negative values in this figure. These are due to the uncertainty, if you will, because these results you are seeing are ran at 100 runs. And when we have more time, we'll run 10,000 runs, and hopefully we will be seeing more stabilized results. Next slide, please.
You have 15 seconds.
Okay, thank you. So in summary, we looked at the stream flux uncertainty, and these are the different findings we had. And more solutes are forthcoming. And this is a product of Quest, which is a research coordination network that dedicates to advancing uncertainty analysis in ecosystem studies. Thank you.
Thank you, Jeff. We don't have any directed questions to Jeff right now, but I think we can move on to our general discussion and take the most of the 13 or so minutes that we have left. There have been a few discussion points that I'll bring up here. I think one of them that was directed towards all the panelists was essentially a question about, have you had dendrochronology work done at your sites? For Marcel, the answer is yes. I've posted 2 DOIs for publications of work that Sally Diamond led at our site a couple years ago. Other panelists for dendro?
I'll just say that we haven't had dendro work done per se. We've done a lot of tree coring for chemistry.
Yes,
Ruth,
Andrew has had dendro work. Plenty of it.
Turkey Lakes Watershed has some as well, most recently done by Steve Volker.
Well, Kryklan, there is ongoing work, and we have now 500 permanent forestry plots across the catchment that will undergo some kind of dendro work. I'm not really sure when and how.
And Ruth Yanai chimed in on behalf of Hubbard Brook, saying that quite a bit has been done at Hubbard Brook. So we have a point from Kevin Bishop, and he's saying that we often think about the big societal research questions that shape the creation and direction of catchment studies. How much have surprises contributed to the developments? Panelists? Well, I'll jump in.
Yeah.
Oh, go, Hjalmar, please.
Yeah, no, I was just going to say lots. I mean, I think surprises is really what drives a lot of our research questions, because that gives us new insights and new avenues to apply for funding to answer new questions. I mean, if there was no change and everything just was the same, continued the same, there wouldn't be much point in continuing, right? I mean, and now when the climate is changing, that gives us an opportunity to look at many things. And then in connection with the decline in acid deposition and many other things happening, I think this is really what drives our interest.
Sherry, do you have a point?
Yeah, I'd second that, because without long-term data, we really can't be measuring these surprises. And so being able to archive long-term data and then revisit it when major events happen or extreme events has really surprised us multiple times at the Andrews.
I think I'd like to throw in too that some of our original questions and design of the watershed studies, the biggest surprise is that we're still trying to answer those questions. They're still relevant. People still want to know. They want us to dig in deeper. So in addition to this serendipity that Hjalmar and Sherry are mentioning, it's also, there's still relevance of the original design and questions, especially when it comes to forest management effects on water yields and water science. Any other thoughts on this? All right.
I just throw in one more thing here, and I think that's a lot of people have mentioned organic carbon and the trends in organic carbon over time. And the interesting thing is that we find different drivers in different places, which has been one of the most interesting aspects, I think, that we need to continue work on, and that connects to a lot of metals and other things. So I think, yeah. I second Sherry's comment there that we need the long-term monitoring in order to actually see something. detect the changes.
Jason Leach would like us to address the, could we comment on what has been the most critical to maintaining success and for ongoing operation of our catchments? I would say relevance. We have to maintain relevance or we're done.
Dedicated people.
Yeah, I think flexibility as well. At least for us, we've had to be willing to go where the money is to a certain extent.
Yeah. I like Kara's use of the word nimble.
Yes.
Giulia Jones has thrown out, how are you addressing the effects of legacies such as past atmospheric deposition and past vegetation clearing and recovery in your research? So how does what happened before affect what we're seeing now?
I think, I'll just say because one of the focuses of Biscuit Brook has been recovery from acid deposition, it's important to qualify recovery in that we're not getting back to something that was before. You're always moving forward. You always have that legacy, and it's important to keep that in mind that, our soils are depleted in calcium. It's not magically going to return just because you turn off the sulfur.
And I agree. I mean, we even in our very remote location up in northern Sweden, we see a recovery from acidification era, and that still provides surprises when we look at the long time series. But I would like to bring up another thing that is quite one of the legacies that is very striking, and the more you dig into it, the more you think it's interesting that so few have looked at it, and that's the ditching era that has occurred at least in Fennoscandia, which is just incredible how much work that it was done in the 1930s, and what the legacy of this is nobody really understands. The channel length of the ditching that has occurred is 2 to 3 times longer than all the natural stream channels and rivers that we have. It's just amazing how much work people put into this. And what does it mean to the hydrology? Well, nobody knows. And I'm sure there are lots of those historical legacies that goes further back in time than we actually think of, at least the Swedes that have a short memory.
Yeah, and I think we're reinterpreting some of those questions of what was the past land use. So we traditionally think on the timescale of European settlement of the US, and that's our baseline. But the forests that existed in the century before we started our experimental forest were not the forests that existed before us. So we know that indigenous peoples in northern Minnesota burned. They made land clearings that isn't a part of our conceptual model of what the forest was in the condition that we inherited when we started our studies. So I think there's a vast room for keeping our research going as we dig deeper and dig in different ways into these questions of what are our sites representative of, and how are the current management schemes that we advocate, are they really relevant to what existed here before?
I'm curious to hear what Giulia Zuecco or Mark and Jeff or Kara have to say about long-term legacies at their sites, and also Sherry, of course. But Giulia, what are your thoughts?
Well, we started our experimental catchment in 2012, so we have almost 10 years of data right now. And in our catchment, we are much more focused on the hydrological processes at the really small catchment scale. So then it's by collaborating with the regional agency for the environmental protection that we managed to study like the hydrological response at the long term. And there is this abandonment of the agricultural areas and so on. But for us, it's the interpretation is quite complex right now, because also it's a catchment with dominated by carbonate rocks, so there is a lot of karst, and it's not that easy to interpret what's the effect of the geology and what's the vegetation effect, so the rapid growth.
I'll comment for Hubbard Brook. It's pretty baked into the conversation about the history of the forest. Having folks like Charlie Cogbill working there, who has been a student of the history of forests in the Northeast. But I'll also echo what Mike had to say about the legacy of calcium depletion. It's impossible to ignore it. We had our forest responded. It started growing once we applied calcium to one of the catchments. So it potentially is our limiting nutrient because of this legacy of acid rain.
The one thing I'll add from the Turkey Lakes perspective, and it became clear when I was writing with my co-authors the paper on the trends in the stream chemistry, is that when we started looking at the trends, we saw all sorts of influence of different processes, but it was the processes are so different for each of the solutes, and that it just has led to even more questions that we're asking, and that we still don't have answers to. So I think that that legacy is very important, and it's okay to look at the trends first and start to understand how processes feed into those trends. So you have to start somewhere.
Yeah, and like in New England, where a lot of the talks today were based, it's now 80–90% forest, and a century ago it was 10–20% forest, because all the land was cleared for agriculture. So most of us are living with that legacy, that second growth forest. And it's interesting, like at Sleepers River, we have carbonate bedrock, and so there was little interest in research there in the 1980s, 1990s, when people were doing acid rain research. But yet we still see the decrease in sulfate in the stream water. We have areas of the catchment that have become really acidic, at least until you get to quite a depth in the glacial till. And so it's really interesting to see how some of the processes that were studied, like nitrification, denitrification, mostly in acidified basins, because that's where the catchment research really got its jump start in the 80s and 90s. Interesting to see how those processes work in a high carbonate basin.
Jamie and everyone else, I think we're at the point where we're down to about a minute left here. And I just want to remind you that this is an 8-week-long seminar series, and keep your thoughts rolling from one week to the next. Write down your questions or send them to us. We want this to culminate in a community discussion in week 8. We're presenting a lot of information in every seminar. It's intentional. We're not trying to overload you. We're just trying to introduce you to the wealth of information and sites that exist out there, and with the idea that we are interested in our future and keeping the science bright and blooming. So pull your ideas, keep them coming. Tune in next week to learn more. And again, we're working towards a final discussion of where we are and what is the future, the legacy and the future of catchment studies.
Yep. Well said, Steve, and thank you, everybody. And I guess we'll close it for today. Thanks. See you next week.
Thanks, presenter. Great job.
Good job. Thanks. Bye-bye.